last of the energy and work videos. So what we're going to do here is just kind of tie in a different way to talk about the work energy theorem and what we know about kinetic energy. So first off, an acceleration, again, is just any change in velocity, okay, causing it to speed up, slow down, or to change its direction. And we can cause an acceleration by net forces. Okay, that's Newton's second law. Well, let's say you apply a net force over a given distance. Well, that's just work. Okay, and let's say applying that net force changes the velocity of the object. Okay, in other words, there's been some kind of change in kinetic energy. Well, that can apply then to the work energy theorem, that the work is just the change in the energy. All right, by adding energy to a system, you can pick it up over your head, giving it potential energy, or you can cause the speed to change or velocity to change, which would cause a change in the kinetic energy. So with that being said, again, we can apply that to systems like automobile. When you are hitting the gas, speeding up, that would cause a change in kinetic energy and work being done, but also braking. And that's what we're going to look on here. That if you apply the brakes, all right, then you're doing work. It's causing a force that is causing a change in the velocity. And by changing kinetic energy, all right, you're doing the work. Well, if work is force times displacement, and it's causing a change in kinetic energy, okay, this is the work energy theorem in math form, we can rearrange that to figure out the stopping distance of a car, for example. All right, this is an equation that we can use to solve for that. That the change in kinetic energy divided by the force will get the displacement of that object. So let's apply that to this situation. So in a school zone, its speed limit is 20 miles an hour. That's 9 meters per second. What would the stopping distance be if you were to drive a Ford Focus with a mass of 3,500 kilograms and had brakes that could apply 30,000 newtons of stopping force? Well, we have the following information. We have the following equation. We can take those different things, cause them and change them, and we get that it can stop in 4.7 meters, which is about 15 feet. Not bad. But I know most teenagers and most people in general see stop lines as more of an option. So let's imagine something that you may do instead. Instead of going 20 miles an hour in a position or in a school zone, let's say that you are going to go at 30 miles an hour, just 10 over, not a big deal. All right, let's take a look at the stopping distance then. So we got 3,500 kilograms because it's the same car. We've got a change of 13 meters per second here. And again, the stopping distance is the same. If we apply that information to the equation, all right, then we get a stopping distance of almost 33 feet. Okay, that's a difference of 17.6 feet. All right, that's quite a big difference. So the point that I'm trying to make here, A, again, just another way we can solve the equation. But B, that the stopping distance, since it's dependent on the change in velocity squared, all right, that the stopping distance would be quadrupled if you doubled your speed, or if you tripled your speed, it'd go up by 9 times the amount because you're raising it to the second power. So a small increase in your speed actually causes a very large change in the distance that it takes to stop. And you should just keep this in mind when going through areas with children that could dart out in front of you. That small bit of time you're going to gain by speeding could end up with bad consequences if one of those children were to dart out in front of you. So anyways, that's the last bit of the notes for this unit.